So this will be the first of a little sequence of videos where we talk about evaluating limits analytically, which basically means using algebra. So we're not going to have access to the calculator, we're not going to have access to a graph, we're not going to have access to a table. Now for those of you that are doing some other things with limits, this video and this sequence of videos won't discuss epsilon delta proofs. It also is a little bit prior to us learning L'Hopital's rules, so we won't be doing those either. Later on in your calculus work, you might be able to do some of those things. But for now, we're going to evaluate limits with algebra, no calculator, no graph, no table. Here's the foundation for that. This graph is a piecewise graph, so I took a minute to sketch a graph for it, and the function defined up here tells me that for x is less than or equal to 1, I'm going to graph the line x plus 1. So I know I'm going to have a closed circle with an x coordinate of 1 and the y coordinate of whatever I get when I take this 1 and I put it in place of this 1. 1 plus 1 is 2. So you see my closed circle with an x of 1 and a y of 2. Now I'm going to have an open circle also with an x coordinate of 1, and I can find the y coordinate for it by plugging 1 in place of this x. 1 plus 3 is 4. So you see my open circle has coordinates 1, 4. I've got the line with a slope of 1 working off of that graph for the x is bigger than 1, and then this line also has a slope of 1 working backward for the x's that are less than or equal to 1. On this screen, if you're evaluating limits, now I know we have a graph here, but the graph should be able to be used to allow you to make a pretty significant judgment. There's only one x value that you should be concerned with the limit not existing for this particular piecewise function, and that's where we have the potential for something weird to happen. And in this case, we do have a jump in the graph. At the x of 1, we jump from 1, 2 up to 1, 4. Because of this jump in the graph, the limit on the smaller side of 1 is going to be 2. The limit on the bigger side of 1 is going to be 4. The one-sided limits don't equal each other. That tells us that the general limit, as we approach 1, is going to be one that does not exist. Now check out these other two limits. These limits I would consider to be trivial. Limit as x approaches 50 for this function. Now I know our graph doesn't extend over on the x-axis to positive 50, but you should be able to convince yourself that because of the only split in the definition of this function being at 1, there's not going to be anything weird happening on the graph of this function at 50. I just need to know the y value from the appropriate piece of the function, and for an x of 50, we would be dealing with this bottom piece, right? 50 is greater than 1. So if I take 50 plus 3, that gives me 53. I don't need to see the graph to determine that. I just know based on the only weird spot on this graph being at the x of 1 that nothing concerning is going to be happening at the x of 50. Similarly, limit as x approaches negative 15. Negative 15 is obviously out this direction a little ways. We don't see the graph extended out to that spot, but there's not anything concerning potentially going to be happening at that x. So all we need to do is specify the y value from the graph at the x of negative 15. That's going to be the answer to our limit. So I would have to go to the first portion of the piecewise function here. Negative 15 is less than or equal to 1. Negative 15 plus 1 is negative 14. These limits right here I would consider to be trivial. There's not a lot to them other than confirming nothing weird is going to be happening and getting your answer to the limit. That notion is going to work together with some of the properties that you see across the next couple of screens. So you would definitely talk about these properties early on in your limit unit of your calculus course. So if you look at this screen here, we've got two limits as x approaches a, one for f of x, one for g of x. They both exist, and then c is going to be any constant. What I can do with a constant when it's inside of a limit is I can factor it out in front of the limit. We'll use that property in a minute or two. If I have two functions added or subtracted within a single limit, I can break that up into the sum or the difference, same operation as what you had initially, of the two individual limits. Same thing applies to multiplication. Multiplication within a limit can be broken up into the product of separate limits. And this is the one you do have to be cautious of. With division, you can break it up into the division of the first limit divided by the second limit. You have to worry about potential for division by 0. So this one you do have to be a little more cautious with using. Now this next screen has a bunch of what I would consider trivial limits. All of the functions that you see on this screen, sine of x, cosine of x, e to the x. Think about the graphs of sine of x, cosine of x, e to the x. You don't have any jumps in those graphs. You don't have any holes in those graphs. You don't have any asymptotes in those graphs. So all we have to do to find those limits is evaluate at the value x is approaching, kind of like we did with that piecewise limit a few minutes ago, and get our answer. We do have something similar mentioned about natural log of x. Now there's a little caveat to this one. I can't put 0 into a logarithm. I can't put negatives into a logarithm. So as long as I'm within the domain of the logarithm function, I can do the same thing for it. Because on the portion of the graph of natural log of x that we can actually see, there are no holes, there are no jumps. There is a vertical asymptote on the left edge of it, but that's kind of the border of the domain. That's at the end of the domain. These two up here, inverse sine, inverse cosine, they don't have large domains. The domains of them would be -1 to 1. But as long as we have a value of x that we're approaching that's within the domain of the function, we just evaluate the original function at the value x is approaching. Same thing for inverse tangent. Same thing for polynomials is listed here. They've separated this little blurb about roots here because if you think about it, you can't do a root of an even indexed root of a negative and get a real number. So that's why this is kind of hashed out a little bit differently. As long as n is any positive integer, then the nth root of the function as x approaches a is going to be able to be found by doing the nth root of the limit of f. And if that's equal to L, nth root of L gives you your answer. But when n is even, L has to be positive. This does not work with an even index and a negative underneath. Now, all these properties might seem overwhelming, right? We looked at these ones here, and then we looked at a bunch of these trivial limits. What's the significance of this? How do I use this to my advantage when I'm evaluating limits? Got a limit here, kind of a crazy equation, crazy function that is within the limit. So 5 e to the x divided by cosine of x minus sine of x times natural log of x plus square root of x. So we've got a lot of the things happening that we've discussed over the last couple of screens. How do we use these properties and these trivial limits to our advantage? I don't have to worry about multiplying by a constant. I'm just going to take whatever the limit of e to the x as x approaches pi is and multiply it by 5. I do have to be a little concerned with division. So I'm going to break this up into whatever I get for the limit as x approaches pi of cosine of x, which is cosine of pi. As long as this denominator is not 0, we're going to be okay with doing this. I'm going to then subtract off the limit of sine of x as x approaches pi, so sine of pi. I'm going to multiply that together with the limit of natural log of x as x approaches pi. And then I'm going to add on to that the square root of pi. So I'm essentially just putting pi in place of all of these x's. And honestly, when you're evaluating limits analytically, that should be your first step. And what you hope happens, doesn't always happen. We'll have some other videos that explain some other strategies you may eventually have to use. But what you hope happens is what happens here. Evaluate this expression right here. I've got the unit circle shown at the location pi. Cosine is going to be the x-coordinate from that point, has a value of -1. Sine is going to be the y-coordinate of that point, which has a value of 0. Don't know what natural log of pi is, just copying that in. Don't know what square root of pi is, I'm just copying that in. I don't know what 5e to the pi is, so you see that that is copied into this fraction again, but I do know if I divide that by -1, it just makes that numerator negative. 0 times natural log of pi, that piece goes away, and I end up with plus square root of pi. This is an ugly answer. That's by intention. Ugly function, ugly value x is approaching. Let's try to confirm that this is okay, what we've just done. So on the next screen, what I have is I have a graph that I built on Desmos. Let me enlarge this a little bit. So I have a graph that I built, actually, no, you can't see it all, on Desmos. So if we locate 3.14, and if you're looking at the scale on the x-axis, looks like that's 3.1, 3.2, so 3.14 coming straight down to the graph somewhere, right in that range is where we have 3.14 on the x. if I think about coming across from that location over to the y-axis, I'm looking at negative 100, a little bit past negative 100. I guess this grid line would be at negative 120. So somewhere between negative 100 and negative 120, a little closer to negative 120. If you evaluate this answer that we got, negative 5e to the pi plus square root of pi, on the calculator, you get negative 113.9. Kind of syncs up with the graph that we're looking at here. Limit doesn't have anything weird happening on the graph. As long as you're not approaching a value where you have the potential for something weird to happen, you can find the value of your limit by simply plugging in. Now, in conclusion, and this is going to kind of be the launching off point for a few of the other videos in this sequence, what signals when a limit's going to require a little bit more analysis than what we've discussed within this video? That first function that we looked at, that piecewise function, it had a jump. Now, it was pretty obvious where that jump was based on where the function was split at the x of 1, specifically for us earlier. But a piecewise function, you have to worry about something like this happening. A limit not existing because you have a split in the definition of the function. Absolute value functions really are piecewise functions, essentially. You can always rewrite an absolute value function in a piecewise form, so you do have to worry about jumps in your graphs if you have one of those components, either a piecewise function that you're considering within your limit or an absolute value function as the definition of the function. You do have to worry about holes in graphs. 0 over 0 is something we'll talk about in detail in one of the upcoming videos. You look at this location right here. That location looks like it's at the x of 1. I do approach that open circle from both sides of 1, so it seems like the limit exists. It seems like that limit would be 2. But how do you identify that for whatever function's graphed over here, that my limit as I approach 1 is 2 without relying on the graph? Upcoming video will discuss that. You also have to worry about vertical asymptotes. So a vertical asymptote would be a location where you have division by 0, but it's not necessarily 0 divided by 0. It's something that's non-zero divided by infinity, which gives you an answer of either positive infinity or gives you an answer of negative infinity for your y value. So we'll have the videos that I've kind of described upcoming. Check those out for more on this strategy.